Let's talk about attenuation in optical fiber and signaling. So the reason why we have to learn about this chapter actually all thanks to Charles Kao. We actually talked about him in the last previous video, and I'll get back to you on this later on. So for attenuation, it's very simple. Usually, as you know, I will ask you to read the textbook, but this time you really don't have to because it's just really simple concept. So let's go through that with me. So basically the ideas of attenuation could be applied in a lot of places. Here we're talking about the power in the optical fiber or in the wire. We could also talk about attenuation in terms of sound. In fact, some of your IA was talking about the attenuation also, talking about how sound will be reduced by maybe different medium or by adjusting different power, etc. So attenuation is just simply a measurement using the log scale. So I'm sure all of you have learned log scale in mathematics. If you don't, let me know. Okay, I will try to talk about that in more details. But I suppose you know the basic operation of log. So let's say log x equal to a, then a 10 to the power of a equal to x. Okay, something like that. Or you should know that log a plus b equals to, log a times b equals to log a plus log b, something like that. So basic operation you kind of have to know, not very difficult. You will see later on, but you have to know about the basic idea of log function. The definition of attenuation is written here. So power loss, which is attenuation, equal to 10 times log P final over P initial. So that means the ratio of the final over initial. And the textbook actually said this is a negative quantity. Actually depends. But of course, whenever we talk about attenuation, then it's always negative, because over the distance you must have less energy or less power, because it just got lost in some other places or for certain reason. So usually it's negative. But let's say if you have an amplifier, then it could be positive. So don't worry about too much about this first. Okay, and the reason why we use log scale is because in reality, the power, if you simply use a linear scale, then it will be very hard. We have to count a lot of zero in that case. But we don't want to deal with all those zero. We rather count how many zero are there. So we use a log scale to help. Okay, so let's take a look of an example from the textbook. So it said if 8 milliwatts has been reduced from the given value. So what you can say is, I should say the power loss is 16 dB. dB, by the way, is decibel, which you may sometimes hear about this in terms of sound. When people talk about the sound in how many decibel, that is also a log scale. So what you have to do is simply substitute the whole thing into the equation. You know power loss is 1.6, 16, and then divide by 10 is 1.6, and then you get the original one, 8 milliwatt here, and then you can find the final power, which is 0.2 milliwatts. All right, it's very, very simple. So let me give you some more examples. You may want to pause the video now, and then we will continue. Okay, so like I said, it's very simple. Just apply the equation. In fact, when you see attenuation in IB exam, you should feel very happy because it's really very simple. So what you have to do is that the question already told you that the power, the signal got amplified from this to this. So just to make sure you get P1 and P2 correct. So P2 is higher one, 2.2. P1 is 0.34. Just substitute and you find the answer. Should be 8.1 dB. If you try to look at the answer from textbook, which is also the same, 8.1 dB, but the thing that I want to point out is the textbook mentioned one very interesting fact that you may want to, it's quite easy to remember, and if you want, you may want to share with other people who don't actually study physics, is that when we talk about in dB, decibel, once again, an increase or decrease of 3 dB may not be a lot. For example, if we talk about the sound, once again, I'm pretty sure you have seen something like a scale and the example like this when you were learning junior science. And for example, when we are talking, for example, now I'm talking conversation, so I think my sound is probably around 60-ish decibel, and then maybe when you are using your hair dryer is 90 decibel, and usually it's quite noisy already. And if you have ever been to like near the airport or even seeing the fireworks, then that will be quite painful, and that's called the threshold of pain. That means beyond that, or I think it's around here. I mean here, yes, the orange or red area here is not a good environment for you to stay in. But if you imagine, so how would that mean in terms of power? Then you can easily tell, because if you try to look at the scale here in terms of intensity, you can see it's not really about the number here, it's more about the order of magnitude. This is milliwatt, this is microwatt, this is nanowatt. So you can see it's talking about 10 to the power of negative 9, 10 to the power of negative 6, 10 to the power of negative 3, and 10 to the power of 0 in that case. Alright, so you can see each of these has like 1,000 change when the decibel changed by 30. Okay, so here is a good estimation for you to think about. Hey, when sound intensity or even the signal got changed by 3 dB, the power actually got double in that case. So it's actually quite surprising if you think about that. Let's try one more example. Here, there's one new but simple concepts that you can think about, which is called the specific attenuation. If you recall the word specific, once again, you learn it in chapter 8, which is about specific energy, or in chapter 3, thermal, specific heat capacity. And if you recall that all of these words, when we talk about specific, it's talk about per mass, right? For example, specific energy is referring to the unit of joule per kg. For specific heat capacity, it's talking about joule per kg per degree Celsius or Kelvin. So here, however, we are not talking about kg, we are talking about the length. So L here, so you just have to divide it by the length. And in our case, it will be per km. Or I don't know why it's not in meter for SI unit, but I think the reason is simply km is a more realistic number, so that we don't have to deal with so many decimal places. Okay, so pause the video now, try this word example. It's very easy also. Okay, so here is the answer. What you have to do is, I will use some annotation, use some symbol I should say. By the way, I think I use it already here. A is actually, I don't think this is a proper official symbol. Actually, I cannot find, I tried to Google it, I cannot find the symbol for attenuation. So I just use A for now, okay? But I think in exam it's better for you if you can simply spell the whole word attenuation. Probably once you need for one time. So AS here would actually mean specific attenuation. So if you multiply it with S distance, then you get the total attenuation over the long distance. Okay. So since it said the specific attenuation is 4 dB per km, for the first time to teach you, so I will write down the unit as well, dB per km, and it is 6 km. So if you multiply, then you get dB. So dB, and the number is 24. I will put down as negative because it is a negative change. I mean, it's a decrease over the distance. So when you input that back to the first equation we learned today, then we would be able to substitute P1 as 12 milliwatts, and A is the negative 24 that you get, and therefore the answer you get 0.048 is the same unit as the 12 that one. Right, since this is milliwatt and therefore this is milliwatt also. Some of you may want to say, hey, should I do this 10 to the power of -3? That's fine if you want to do that, but then I would say if you are aware, like if you are aware enough, then you know that this unit and this unit should be the same. So if you don't do anything here, then P2 just follow the same unit as P1, so milliwatt there. Okay. Let me spend maybe 1 minute to talk about more about Charles Kao. Okay, so this is a video I'll put in the description, so you can take a look of how Professor Kao did the experiment to study the material of optical fiber. And I would also like to share this article with you. And I think this article tells us very well about what actually happened and why the optical fiber improved by Charles Kao will be very useful. Alright, as I said in the previous video, he wasn't the one invent the optical fiber, just like Thomas Edison wasn't the one invent the light bulb. But Charles Kao's work actually is very important, so that's making the optical fiber practical. So let's take a look here. So in 2009, he got the Nobel Prize in Physics because of optical fiber. But then he actually started to work as an engineer, like I think 40 years right before he get the Nobel Prize. So it's actually many years to go. And then he was apparently studying attenuation. This actually means attenuation. And at that time, you can see here, the optical fiber has 1000 dB per km. Can you imagine like what is that? -1000 dB per km. The one that we just did was what? 4 dB per km. Alright, and later on you can see more example. Alright, none of those questions talking about 1000 dB per km. So if you are having a number like this, basically means your optical fiber is useless. Okay, so at that time, the so-called optical fiber is basically useless. And because of that, so many other scientists, you can see here, so many other scientists did not ever thought of that would be useful. So like in America, that they already thought maybe that is not useful. Maybe they should just study the metal. In fact, if you know about in the past when people have the optical fiber for network, in the past people use the telephone wire. Maybe you don't even know what telephone wire is. Telephone wire is talking about like domestic home. Probably you still have a telephone, but actually I don't for now. But maybe for like 10 years ago, I think everyone's home would still have a telephone, which is connected to the wall. There's a socket, so connected to the socket. So your phone, you have to dial number, etc., like the physical phone. And one special thing about internet in the past, or network in the past, is we don't use the LAN cable from now. What we use is actually we have a device, and then it would take the signal from the telephone network. And people call this 56K at that time. All right, if you try to search 56K then on Google, then you'll find some more pictures. So the special thing is, in the past, people like to play online games, and when they play online games, usually like more like those kind of competitive online games where you have to maybe versus your friend, etc. And what happened to the usual young people is that when there's a very stupid thing happened in the past is when you are almost losing, of course right, before you surrender in the game, what you could do is you can somehow find a way to call your friend. Apparently your friend's phone number, and then once you call them, because the technology was not advanced enough, so what happened is their network will be down in that case, so they simply would just get disconnected. So the game is basically got ruined. So so it's not a win or not a loss in that game, and that was something that was very annoying back that time. I think it's around 1980s or 1990s, right, back that time. Nowadays, of course, it's not, right? We use a separate LAN cable for that. Okay, back to the story here. So Charles or Professor Kao did not give up on that, and he thinks if we can reduce the specific attenuation to 20 dB per km, then surely we can use it for communication. And so at the end, I think he approached another guy. This guy is quite strong in terms of the material, and so they eventually they will be able to use as, I think, something very special, using something like silica. It's very specific, like it's not a natural thing you can make. You have to artificially make it, and at the end it got improved until I think in 1979 the specific attenuation is already 0.2 dB per km. And I think by that time it was used for military use, and then later on it will be used for like household, I mean domestic use, instead of the copper wire. So copper wire was used in the telephone wire in the past. Yeah, and like I said in the previous video, the most respectful thing is he did not get any money from this. All right, you know, people always try to get those license, patent, and try to earn money from it. But Professor Kao actually didn't do that, and he just wants to improve the quality of life. So that is really respectful work from him. Let's move on to the next question. Try this out, pause the video, and we'll talk about it. Okay, here this is a quite interesting question. It basically tells you another situation where you know the specific attenuation, so AS, and it's set. If you actually know something about like Wi-Fi at our school, I mean, for Wi-Fi at your home is usually easy. I mean, it's usually simple because, especially in Hong Kong, I think at least not ordinary people like us, your home will not be that big. So usually one router, I'm not sure if you know, I think you should know, right? Router is the one that emits the Wi-Fi. One router will be enough. And so for places like company or school, like our school, then we of course we cannot rely on one router. So there's something called access point, which is acting more like amplifier, and so they basically amplify the signal. So you have to simply install more in order to get more places to get the Wi-Fi. For example, if you go to like our rooftop, you find out the Wi-Fi signal may not be as strong comparing with maybe third floor. So here it says 10 to the power of 18 is talking about when P2 over P1 is decreased by 10 to the power of 18, and so this is like what is the value, like the value of this. I think it should be other way around actually, but what you do is put a negative outside, so it's actually fine. And then find out the distance. So S is a distance. So what you have to do is simply use attenuation to relate the two equations. As we learned, the attenuation equation is 10 log P2 over P1, and at the same time is specific attenuation times distance. Then you can simply substitute this into P1 over P2, and then AS is 3, and you find the answer as 60 km. Alright, so it's actually quite, I would say actually quite interesting question. There's another thing that mentioned by the textbook is that for specific attenuation, it actually depends on the wavelength once again. And you can see there's a graph here. Alright, this is obtained by experiment apparently. I don't think we can explain the reason why, at least for now, I don't know how to explain like in a more fundamental way, but at least this is the experimental result. And normally you may expect, hey, I mean, think about if you're doing your IA, usually you expect a trend like this, right? The red line that I draw. But then very strange thing is that the attenuation somehow is different here. Alright, you got somehow higher here, lower here, and lower here. So what it said is at this graph, you can see the specific attenuation is somehow lower at these two wavelengths. And that actually means if you want to send a signal, you don't want that much attenuation, right? So if you could choose this wavelength and this wavelength, you simply get more advantage. So maybe these two would be a more desirable or optimal wavelength for transmission. And somehow these are infrared. All right, so if you try to check the wavelength, these two belongs to infrared, comparing to those shorter wavelengths. Try this question. This question is actually very interesting, and basically this is the best question I would say among this video and textbook as well in terms of attenuation. So pause the video now, try it out, we talk about it. Okay, so for these questions, what I would do is I would firstly, this is not a question that gives you a real number, right? Giving you any actual number. So what you have to do is I would firstly define the power as P1, P2, and P3 here. So apparently before earliest is P1, in the middle is P2, and later on is P3 when it's out. And what you can write about is, over here, the first line you can write is G1, which is the amplifier here. What it does is changing P1 to P2. So the equation you can talk about is 10 log P2 over P1. Same for the second amplifier. So G2 equals to 10 log P3, because this is the final P3, and before was P2, the input is 2. And so this is the two equation you can write about. And the question is asking you about the overall gain. So overall gain, I use GT, total gain, to represent. And apparently, you can imagine we just care about the input and output. We don't care about the middle, if that's the case, okay? When we talk about overall. So P3 over P1, in that case. And here is one special trick you can do, and it's very normal and often seen in maths, is you multiply the P3 over P1 with 1, which equals to P2 over P2. Alright, you can do that apparently, because it's the same number. And the best thing is then you can group P3 over P2 and P2 over P1 separately. And as I said at the earliest of this question, this video, log A times B is log A plus log B, and therefore you can split this to 2, become P3 over P2 and P2 over P1 here. And then again, the best thing that we can find is, if you try to expand it, you just simply find this is G1, this is G2. Isn't that amazing? If you think about that, that means whenever you see the decibel scale, you can simply add them up together. Okay, here is talking about the optical fiber signal. When we talk about sound, then that would not be the same. All right, be careful. It's not going to be exactly the same, because we are talking about amplifier. But anyway, all right, for optical fiber, we could simply just add them together. Okay, this concept will be very useful later on. Okay, so where are we at? Here. Okay, so let's try this question. Pause the video. We'll talk about it. Okay, this is a simple question, so I'll just try to go through it quickly. You want to find the attenuation per unit length, that means specific attenuation. So find attenuation first, and then you know P2 and P1. Substitute it, you find attenuation is actually in dB, and then you divide by the distance, 25 km, so you get the answer in dB per km. Very simple. Try the next one, pause the video. Okay, so here is also another very simple question. So it sets the signal when it falls to 70%. So that actually means that P2 over P1 is 0.7, right? Because let's say originally it's 100, 100, and now it get to 70, then that would be 0.7. So what you have to do, similar to the example that we did, simply P2 over P1 is 0.7, and you use the attenuation to link the two equations, 10 log P2 over P1 and specific attenuation times S. You substitute the AS as well, you can find the length, which is 129 meter. Try this question. You may want to use, the question I talk about, you can actually combine them to find out the answer much quicker. Pause the video now. Okay, so first of all, let's take a look at what the question is asking you. So it asks you the ratio of output to the input. That means P2 over P1. Okay, and the second thing is using the trick that we just mentioned. Is actually, well, what you have to do is simply add them together. So positive 15 plus negative 12 actually gives you positive 3. And by the way, this is the reason why we use a log scale and setting up the attenuation equation, A equals to 10 log P2 over P1 this way, because only in this case then we can add up all these things so easily, right? And it will be very, very handy. So since you know it's 3, that means attenuation is positive 3, that means you actually gained more power. And so you just try to find out the ratio of P2 over P1 using this equation. You solve it, you find out it's roughly 2. And by the way, this is basically what we said earlier. That's when you have 3 dB. This is about a double of the power. Try this question now, pause the video. Okay, this is probably the easiest question ever in this book. It asks you to find out the ratio of output power to the input power under like this setting. So you have 7 positive, 10 negative, positive 3. You add them up together, you find out the total gain is 0. Right, it's 0. It's just 0 directly. So that means that the total power output and total power input has no difference. That means it's equal to 1. So yeah, so that's basically what you have. Let's try the next question and pause the video now. Okay, so here is somewhat similar to what we did. First of all, it said from the question the output is the twice of the input, so P2 over P1 is 2. That's the information. And it also means if you try to use the equation, or if you simply remember the result that we mentioned earlier, if the power is twice, then that actually means the attenuation would be 3 dB, or you can substitute to the equation again if you forget. You don't have to memorize it. It's positive 3 in this case because it's output higher than input, so positive 3 in this case. And so after that, you just have to look at the gain over the amplified, and that will be negative 12. All right, terrible color. Negative 12 plus G minus 6, and that overall should equal to what you find out earlier, positive 3. And you just solve it and you'll find it's 21 dB, right? Positive, of course. That's all for this part of video.